Hello, my name's Alex Cameron. I've recently finished my PhD at the University of Melbourne, and I've just started a postdoc at the University of Oxford. And I'm going to be talking about some work from my PhD, measuring extra-planar electron temperature variations at the base of an outflow in Mrk1486 with the DUVET survey. So electron temperature is a very important parameter when studying ionized gas, particularly when we're looking at chemical abundances. Measuring electron temperature requires, though, detections of these faint auroral emission lines, in particular this OIII-4363 line. And so this makes electron temperature observationally very challenging to measure. However, modern instruments are improving this situation. And so what I'll be showing you today are some early results from Keck KCWI data taken as part of the DUVET survey, in which we're able to map out the electron temperature in an edge-on system. So the system that I'm referring to is Mrk1486, shown here, which is this relatively low mass starbursting galaxy. So the critical emission line that we're searching for is this OIII-4363 Aurora Line. And we can see here that with the KCWI data from DUVET, we're able to map this out not just with tenuous detections, but really we're getting booming detections of this auroral line over quite a large spatial extent. So we can see here a temperature map for the spatial region in which we can detect our 4363 auroral line. And so you can see that we can do this for about 4 arc seconds along this minor axis direction, which corresponds to around about 3 kiloparsec. So on the left here, I'm showing this as a temperature profile moving along the minor axis for this region bounded by the dotted lines shown here in the map. And so we can see here this pretty clear temperature gradient where we're seeing the electron temperature decreasing as we're moving away from the disk. And so we can see this particularly clearly in the right-hand direction, perhaps less clear in the left-hand direction, although I think we are perhaps still seeing that. And so a decrease in the temperature is usually associated with an increase in the metallicity, but given that the ionization conditions of the gas are also likely to be changing as we're moving away from the disk, we looked at how these observations compared to predictions from photoionization modeling. So what I'm showing here is a plot of 2 different emission line ratios. So on the vertical axis here, we have our auroral line ratio, which essentially corresponds to the electron temperature. And then on the horizontal axis here, I'm showing the O3 to O2 ratio, which will loosely correspond to the ionization parameter. The scatter points here are our DUVET observations for Mrk1486, focusing on this region on the right-hand side, moving away from the disk. And the color bar here is indicating the distance away from the plane of the disk. The colored squares are then showing the predictions from mapping's photoionization model grids, where each line is a line of constant metallicity for 3 different values of the metallicity, and the color coding indicates different values of the ionization parameter. And so if we look at the observed points from Mrk1486, you can see they form something of a sequence starting here at the plane of the disk, and then as we move away, we're moving down to lower temperatures and lower ionization parameters, moving away from the plane of the disk. So according to the mappings grids, if this decrease in temperature was only due to decreasing ionization parameter, these points would follow the gradient of this line of constant metallicity. But we can see here that at the highest distances, these points are tending to dip below this line. And so we take this as evidence for an increase in the metallicity as we move away from the plane of the disk in Mrk1486. And so we think what we're seeing here may be an indication of the effect of metal-enriched outflows in Mrk1486.